Okay, we are going to, before we get into Chapter 10 next week, we want to do a review of statistics. Now, it's been quite a while since you've probably reviewed this stuff. I've been told that this is material that you haven't quite really been taught since, or have gone over since Secondary Mathematics 1. So it's been a while, so we're going to do a review, go over some definitions, some terms, and yeah, that will help us prepare for next week. So, there are some definitions that I want to go over. So, let's go over these definitions first. So, in statistics, statistics is a lot about data. It's about analyzing, and it's about gathering, analyzing, collecting, organizing data. That's pretty much what statistics is. And there's a lot of terms that help us describe the way that data is behaving. And so that's what a lot of these definitions are for. So, for instance, the mean. The mean in a set of data is the average of the data. So we'll call this the average. Mean is the average. The average number, the average of the data set. Okay, and it's usually denoted. It depends on where you're collecting your data from, but the mean can be denoted by with the Greek letter mu. So it looks something like this. It looks like a U, but it also has a tail, a long tail on the left of it. Okay, so this is mu. Or you might see the average represented as x bar. So it's x with a bar above it, with a line above it. Okay. Now you can find the mean or the average. So it's found by taking the sum taking the sum of all the data and dividing by the population size. Dividing by population or sample size. And we usually denote population and sample size with n. Big N or little n, depending on which one we're talking about. But this is basically just saying the number of how much we have. So if you wanted to find the average of the test scores in a class, you take all the test scores, you add up all the test scores, and then you divide by your size. So in that case, it would be by the number of people who took the test. So if we were to think about the last test that we took, we add up all the scores from the last test that we took and divide it by the number of students who took the test. And that would give you the average or mean. Now let's talk about the median. The median is the middle number So the middle number in a set of data. So it's the middle number in a set of data when organized smallest to largest. Middle number in a set of data when organized smallest to largest. Then there is the mode, which is the number that is most often repeated. The number that is most often repeated in a set of data. most often repeated in a set of data. Okay, now these three definitions, the mean, median, and mode, these three terms are to help us describe the middle of the data. So it's a way to help us to describe where the middle of the data lies. And depending on what our data distribution looks like, it might be better to use the mean, the median, or the mode. And we'll go over a little bit more of what that means. So now the range is the difference. It's the difference between the largest and smallest values. Essentially what the range is just saying it's like you have like test scores. If we were to say our test scores, if the lowest test score out of 100 was 20, and then we have the rest of the data, and then the highest test score we could say was 100, now the range would be 80, because the range is from 20 to 100, which is 80 different values. So that's what the range would be. Okay, and now we're going to talk about a 5-number summary. Okay, 5-number summary. A 5-number summary is, if you have a set of data and numbers, what the 5-number summary tells us, it tells us how the data is spread out. Okay, so the first quartile, we like to separate the data in a 5-number summary into 4 different sections, essentially into 4 quarters. Okay, so that's what a 5-number summary does. Now, Q1 is like it's the marker for the lower half of the. So if we have some data, let me try and make a little bit more sense of this. So if we have a data represented as a box, okay, let's say all our data is within this box, and we split this box up into 4 sections, into 4 quarters. This is essentially what we're doing. So this would be our Q1. So our Q1 is the median of the lower half. Okay, so right here, this would be considered the lower half of our data. So then Q1 would be the middle, which is why it's the 4th marker. Okay, and then that means of the upper half of data, this would be our 3rd quarter mark. So for Q3, we call this the median, or Q3 is found by finding the median of the upper half. And that means Q2 would just be the median of the whole data set. It's the median of the entire data set. The minimum is the smallest, is the lowest value. So that would be right here. So this would be the minimum, and the maximum is the highest. So that would be your max. The interquartile range, or we call it IQR, this is equal to Q3 minus Q1. And essentially what this is, the interquartile range tells us where the middle 50% of our data lies in the 5-number summary. So this right here would be the interquartile range, that highlighted section right there. So I'll just go like that. This is the inner quartile range, and the interquartile range can be found. Let me see if I can get this moved over. The interquartile range can be found by taking Q3 and subtracting Q1. Okay, but yeah. Okay, and then a box and whisker plot is essentially what this is right here. So actually, let me take a copy of this. A box and whisker plot is a diagram containing the elements of the 5-number summary. Okay. And instead of showing this as a box right here, a box and whisker plot will look something more like this, where you still draw your inner quartile range as the box, but you draw the first quarter and the last quarter as what they call are the whiskers. This is to help us show where the bulk of the data is. The inner quartile range shows us where most 50% of the data lies. Okay, so this would be a box and whisker plot. This is what a box and whisker plot diagram looks like. Okay, and it doesn't show it. Well, okay, so let's come down here for just a second before we move on to some examples. But the standard deviation, I wanted to define this first. The standard deviation is the average amount of variability in your data set. So it basically says how far each score lies from the mean. Now I know I'm going to be jumping around a lot in this video from spots to spots because I feel like it's better if I describe this a little bit, but down here on this page right here, your third page, you can see that these curves represent the data, okay? But you can see how different they look. This one is a symmetrical curve where you see how we have low ends over here, but then it's like a hill, like we call this the bell curve. And then over here you can see that it's skewed in a different direction. So what this means is that this is this is why it's important that we understand which means of these definitions mean, because there are different ways to define the middle of a data set because not all data is the same. So right here in a symmetric distribution, this would be where this line right here represents the average. But in a symmetric distribution, the mean, the median, and the mode are all the same. They happen in the same location because the mean, median, and mode is meant to describe where the middle of your data is. But like in something that's skewed right here, like if you have data that looks something like this kind of a curve, the thing is the mean ends up lying a little bit more to the left or to the right of your median, and that's because you have a lot of data that might be skewed right here. So what this might look like, or like what this might look like, let's say that this was a representation of your test scores. So let's say that this was 100% and this was 0%, okay? this would mean that you have a bunch of students that scored really kind of low, but you had the bulk of the students score really high. So this means that using the average score to kind of represent where most students got wouldn't be a very good idea to measure the middle, to give you an idea of how the mean wouldn't be a very good representation of how most students scored, because for students that score really low, it skews our data. So this means that it's the mean is getting further away from the actual middle part of our data. And the mode right here, this is where, again, the mode is where you have the most repeats of a value. The mode would be too far to the right of the middle. So again, not a very good representation of where most students scored. So that's why when you have skewed data in either direction, the median is actually a better way of of describing where most students or where most of your data lies, because the mean and the mode are skewed. But if your data is symmetrical, so let's say right here, if this was 0% and this was 100%, if we're talking about test scores again, well, if the data is symmetrical, meaning that this would be 50%, so if a lot of students got about 50%, and then there were some that got 100, some that got 0, then the mean would actually be a better way to describe the middle of the data. Okay, so it's important to know when to use these. Now let's talk about what this is. So the range, a 5-number summary or the interquartile range, and the standard deviation are a means of describing the variance. Okay, so while mean, median, and mode were words to help us describe the middle, you could say that the range, interquartile range, and the standard deviation helps us understand the spread of the data. The spread or the variance of the data. So here, the bulk of the data is over here. Bulk of the data is over here, where the median is over there. We might have some whiskers over here and some data over here. So this is what a box and whisker plot would look like here. So that's what it would look like. Now, for a symmetric distribution, it would look very symmetrical, where you have the bulk of the data in the middle, the median would be in the middle, so on and so forth. But the standard deviation, what the standard deviation tells us, again, if we go back to the definition of standard deviation, it says how far each score lies from the mean, so the average amount of variability in your data set. So we could call this right here, since it's symmetrical, we could create a mark right here. So from here to here, we could call as one standard deviation to the right and to the left. And then we can do it again. We could say that this is 2 standard deviations to the left and to the right, and then we could say that this is 3 standard deviations to the left and to the right. And what this does is we could say, well, most of the students scored. This right here would be a large percentage of students. If we're talking about our tests, sorry, I should be specific about what we're talking about. So if we're talking about test scores, this would represent where most of the students scored, right here. So we could say that the majority of students scored within 1 standard deviation of the average. So right here is the mean or the average. So most of the students, they were either most of the students were between 1 to the left and to the right standard deviation. And then all students scored between 3 standard deviations. So again, it's a way of describing the spread of the data away from the average. Okay, but the standard deviation is not helpful. It doesn't give us a good idea, an accurate idea of the spread if we have skewed data. So whenever we have skewed data, it's actually better to use the interquartile range because it tells us where the bulk of the data is and where the outliers are. Okay, so that is what spread is. So again, mean, median, mode tell us where the middle of the data is, while the range, the interquartile range, and the standard deviation is a way of describing the spread of the data. So let's get into an example. How many siblings? How many siblings do your classmates have? So let's say we presented this question to our class, and we went around and we saw how many siblings that everybody has. Okay, and let's say this is the data that we receive. So if this is the data that we receive, we want to create a box and whisker plot of this data. So to create a box and whisker plot, we need the 5-number summary because that's what the box and whisker plot is composed of. It's composed of these 5 numbers. So in order to do this, we need to find the median and the Q1, Q2, Q3. To do that, our data needs to be organized in the correct order. So we should organize this in an order from smallest to largest. Okay, so 0 is obviously our smallest number, and I see 3 0. So I'm going to rewrite this. So 0, 0, 0. Okay, have those recorded. And then I see a 1, a 1, and a 1. So that's 3 1s. 1, 2, 3. Alright, I see a 2, 2, 2, 2, 2. So I think that's 5 2s. So 1, 2, 3, 4, 5. And then for 3s, see 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. I see 1, 2, 3 fourths, and then I see 1 5, 1 6, and 1 9. Okay, so I have that ordered there. Now I'm also kind of interested in seeing how many numbers we have together. So this is finding our population size. Okay, so here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, so I think that's right. I think I have 23. I'm going to make sure that I counted. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, so we have all our numbers accounted for. We have 23. So that's our data set. So I'm just going to say n is equal to 23. Again, n is the population size, how much we have. And we want to create a box and whisker plot. Now, we need to find the 5-number summary. So we need to find the minimum, first quarter, second quarter, third quarter, and the max. Now, the minimum is the smallest value, so this one has to be 0. The maximum is the highest value, so this one would have to be 9. Okay? Now, quarter 2 is the median, right? So quarter 2 is the median. So we need to find the middle number. Okay? So I'm not sure how you guys want to do that, but you see how we have 23? We could just go down here. So mark 1 from each side and go down, go down, go down. Might take a little bit more time, but I guess it's a reliable method if you do it right. Okay, so that's how you could do it, but the thing is you'd have to do it, make sure that you do it with this set of data right here. But I think there's an easier way to do this. So you see how we have 23 numbers. if we have 23 numbers, that means the middle number would have to be the 12th number, right? And just to make sure, sorry. Just finding myself to the middle. Right there. Yep, 12. So that is the middle number right there. So this right here is my Q2. My median. So that's the middle of my data set. Now, Q1 is the median for the lower half of the data set, okay? The lower half of the data set. So what I do here, now because it's an odd number, so 23 is an odd number, I am actually not going to include the median. So what that means is whenever I find the middle number here, I'm starting here. So again, doing the same thing as I did before. So cross those out, cross that out. I'm trying to find the middle number here. And so the middle number will be 1. So right here, Q1 would be my middle number of the lower half of data. So that's going to be 1. Okay, and then Q3 will be the middle half of the upper set of data, which should just be right here at 18. So right here, this one will be Q3. And that is 4. Don't know why I wrote Q2 right there. I should have wrote it 12. Okay, so this is not 12, 3. So this is my 5-number summary right here, and this is what I'm going to use to make my to create my box and whisker plot. Okay, so let's see here. So create my box and whisker plot of the data. So I need to make sure that it's to scale. So you see that I range from 0 to 9. So that means I'm going to just make some markers so I know how much I go. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0, 1, 2. So if this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll call this 9. Okay. Now, let's mark where our 5-number summaries are. So here is a marker at 0, right? And then here is the other marker at 9. I have Q1 at 1. I have Q2 at 3. I have Q3 at 4. Okay, and those are all my data. Now, the interquartile range is right here. This is my interquartile range. An interquartile range you draw as a box. So that's right here. And then from Q1 to the minimum, you draw your whiskers. Like that. Okay, now this would be the data set here. This would be our data set. Okay, represented in a box and whisker plot. So here would be the minimum. This would be Q1. This would be Q3. This would be Q2, and this would be the max. Just like that. Okay. Now, creating a histogram of the data is pretty much like the same thing, so I'm actually going to cheat a little bit. I'm going to copy this down here, Histogram is kind of like a bar graph, but not exactly like a bar graph. Okay, so I'm actually going to hopefully that works. There we go. Okay. So a histogram uses bars to show us the data, right? So this should be more like a graph. And then I'm going to number this right here. So from 1 to 6. So this means right here. So like right here, how many times does it show that? Oh, I drew that to the wrong side. So how many students said that they have 0 siblings? And there were 3 that said that they didn't have any siblings, meaning that they were an only child. Okay. Now you had 6 students that said that they had 3 siblings. So that was the highest that it recorded. So I need to show at least 6 up here. So 1, 2, 3, 4, 5, 6. Okay. It's 1, 2, 3, 4, 5, 6. Okay, so again, 0 for students who said that they had 0 siblings, there was 3 of them. Okay, so there would be a plot showing that for those that said that they have 0, there's 3 of them. For those that said that they had 1 sibling, again, that was 3. For those that said that they had 2 siblings, there was 5. For those that said that they had 3 siblings, there was 6. For 4 siblings, there was 3. For 5 siblings, there was 1. For 6, there was 1. For 7 and 8, there was 0. And then we had one that said that they had 9 siblings. Kind of got bored of filling those in with color. But anyways, this is what the histogram would look like right here. So this is a histogram. Like that. And you can kind of see how the bulk of the data is to the left. Okay? The bulk of the data is to the left. Okay. Now, right here, we are going to, this is a way of showing you how to find the standard deviation. Okay? Now, as an equation, the standard deviation is actually, it's quite a process to find the standard deviation. Okay, again, the standard deviation, what we're trying to find is, so if we have, so let's say we had a bar graph or a histogram that looked like this, that was symmetrical. Okay, so if our histogram looks like this, it's actually best if we use the standard deviation, which tells us how far the data is away from the mean or the average. Okay, now standard deviation is denoted with this Greek letter called I think it's called sigma, if I'm correct. I want to say that's what it is, but this is what it looks like anyways. Okay, now the equation for this is as follows: the square root of the sum, this right here, this means sum of x minus x bar squared divided by n. Okay, so that's actually a pretty crazy formula, but we're gonna break it down piece by piece. This is pretty much this is the process for finding the standard deviation of a data set right here. Okay, so this is a way to help you find standard deviation. Okay, so first of all, create a table with this information. So x here means your data values. Here's our set of data values, and I'm going to label it in these boxes from lowest to highest. So 1 to 2 to 4 to 6 to 7. So that's just all these values right here. Plug in for x. Okay. And then x minus x bar. X bar is the mean, if you guys remember that. This is the mean. So we need to find the mean right here. So the mean is found by taking your values. So let's do 1 plus 2 plus 4 plus 6 plus 7 and divide that by the number of values that we have, which would be 5. We have 5 values. 1, 2, 3, 4, 5. And when we do that, I believe we should get 20 divided by 5, which is equal to 4. Okay. So that is our mean. This is equal to x bar. So what we want to do is do x minus x bar. So if this is x, we want to subtract 4. So we'll do 1 minus 4. This would be equal to negative 3. And then we do 2 minus 4, which is equal to negative 2. 4 minus 4, which is equal to 0. 6 minus 2, or 6 minus 4, which is equal to 2. 7 minus 4, which is equal to 3. And then here, it's asking that we square these numbers right here. So let's square these numbers. So negative 3 squared is 9. Negative 2 squared is 4. And then there's 0. And then it'd be 4 and 9 again. Okay. So again, that's like this part right here. That's what we just found. Now this means add them all together. So this is the sum. It wants us to find the sum of all of these numbers, the sum of those numbers. So if we add these all up together, we should get 26. Okay, and then we take that sum and we divide it by n. So n is the number of values that we had, which was 5. So 26 divided by 5. Okay, 26 divided by 5. It's about 5.2. And then take the square root of that. So square root of 5.2. So let me go to my calculator. When you do that, you should get that it's equal to about 2.28. This right here is your standard deviation. Okay, and what this means is, so we said that our average was 4. So if we had a diagram and if our distribution looked like this right here, our average would be 4 and the standard deviation would be 2.8. So one standard deviation to the right would be 4 plus 2.28, which would be 6.28, right? And then you could go again for another standard deviation, and then you can go to the left and the left. Okay, so it's seeing how much the data is going away from the center. Okay, now I want you guys to try the same thing that we did here. Again, just use the process that we did here. Add your numbers, your values right here. Okay, find the mean and take these numbers and subtract the mean from it. Square that number. Take the sum of these numbers, divide this number by n, take the square root of that number, and that's how you find your standard deviation. But we're going to keep going. Okay, so here's a situation. It says the average salary for players on the LA Lakers team is about $5 million, and the average salary for a player on the Portland Trail Blazers team is $4.173 million. Based on only this information, which team would you rather play for? So based on this information, again, you're seeing average. Okay, so the average player, I guess you could say, on the LA Lakers team, it's obviously higher, right? So by looking at that, you might think, yeah, I would rather be on the Lakers team. The average player has a higher salary than the Trailblazers. Okay, so I guess we could say, based only on this information, yeah, the LA Lakers. Although you would never actually really ever want to play for the LA Lakers because they're the worst. But just if we're talking about data and trying to be objective, sure. Okay. Is the average a good measure of center for these teams' players' salaries? And I would argue that it wouldn't be a good measure of the center. Mainly because we have what are called outliers. So on the LA Lakers, there are two big stars. You have LeBron James, right? LeBron James and Anthony Davis. These are two huge, massive stars that probably are well above this mark right here. Okay. Okay, probably well above this. I'm pretty sure that LeBron James has a salary of something like $39.22 million. It's pretty crazy. He has like it's insane how much he's getting paid. But him and Anthony Davis probably are well above this number. Okay, what that means is it's skewing the data, making the average seem higher than what it actually is for most of the players on that team. Now, it's probably the same thing for the Portland Trailblazers. You have stars like Damian Lillard, CJ McCollum, but they probably, I would doubt that they get paid as much as LeBron James and Anthony Davis. So, I would say no. You don't want to use the average to measure the center because LeBron James and Anthony Davis are huge outliers. So it's making the average seem higher than what it actually is. So what would be a better measure of the center of data? Probably the median. Probably the median would be a better way because the median doesn't take into the account, well, it's not affected by outliers. The median is not affected by large outliers where the average is. Okay, and so whenever a lot of students, they'll ask me for the average or the mean of a test score. Now that's kind of difficult to say because if I account for students who didn't take the test or students who don't study for the test, and there's actually quite a few that do, there's actually a lot of students that end up so if students get really low grades, that pulls the data, it makes the average seem lower than what it actually is. Because most students actually do pretty okay. They probably score between 65 and 80%. Most students are within that range. However, there are probably about 5 to 3 to maybe like 3 to 7 students that either don't take the test, which results in a 0, or they perform really bad because they didn't study. So what that does, those outlier scores pull the average down. So again, if I were to show you like a histogram or a box and whisker plot of the data of your test scores, it wouldn't be symmetrical, meaning that the average wouldn't be a good way, or the average or the mean isn't a good way to measure the center or where the most of the students actually scored. So it's actually better if I give you the median grade rather than the mean. Okay, so an outlier, So when I ask for an outlier is like I just described. it's something that kind of pulls the data away. An outlier is an observation. I guess the official term is an observation. That lies outside of the overall pattern of a distribution. Okay, that's an outlier. So again, LeBron James and Anthony Davis, their salaries are outliers, meaning it's not the majority of players on the Lakers team probably don't get paid nearly quite as much as what they do. They are outliers. So here it's going to help us try and find data with and without outliers. So you see here number 1, so first circle the outlier in each problem below. So you see how we have 3, 2, all the way to 6. This is probably where most of the data is. 16 would be the outlier. 16 is definitely the outlier. It's much higher than where most of the data is. So 16 is the outlier. Now we want to find the mean, median, mode, and range with and without the outlier. So if we want to find the mean, we have to add all these up together. So I'm going to order this in a better order, so from lowest to smallest. So 2, 3, 3, 4, 5, 6, and 16. So if we're talking about without the outlier, so ignoring the outlier for now, we want to add these up and divide by 1, 2, 3, 4, 5, 6. So add those up and divide by 6. So when we add those up, I think we get 24, and we want to divide by 6. So the mean would be 4. With the outlier, so if we do 24 and we add 16 to that, that should be 40, and this time we divide by 7, because that's how many numbers we would have, we would get 5.7. So you see how the mean is the average of these numbers goes up by almost 2 values when we include the outlier. The median, so if we were to find the median, so find the middle number, so those go, those go, those go. So with the outlier, the median is 4. Without the outlier, so you see how the middle number, there's actually 2 middle numbers right here, 3 and 4. What this means is you take the average of these 2 numbers. So what's in between these 2 numbers pretty much. So you add those numbers together. So 4 plus 3, which is equal to 7, divide it by 2, which is 3.5. So that would be the median here. Okay. The mode, that's the number that repeats the most often, so that would be 3. Okay, now the range without the outlier would be 6 minus 2, which would be 4. With the outlier, that would be 16 minus 2, which would be 14. Okay, so you see here how outliers really affect your data. Okay, now again, without an outlier, the mean is a better way of describing your center. So without the outlier, yeah, we could say that the average for this data is 4. But if we're including the outlier, we don't want to measure the center with the mean, but with the median. And you see here how it's actually the same. So meaning that the median with outliers is a better way of describing the center of data. Okay, and the mode is 3, and then the range, you can see how crazy different the range is. So range is supposed to describe how far the data is dispersed. Now the data actually isn't that really dispersed without the outlier, right? Without the outlier, there's really not a whole lot of variance within the data. But with the outlier, there's a lot of variance. So which is why when you're using, if you're debating on whether or not to use the range, interquartile range, and the standard deviation is better without an outlier. But with an outlier, it's better to use the range. Okay, so you guys can try number 2 right there, just using the same method that we did. Okay, and then we already went over this, but I do want to cover one thing, because when we're talking about data that's skewed, positively skewed distribution, you could also, a lot of people say, this is basically means the same thing as being skewed to the right. And then negatively skewed distribution is skewed to the left. Skewed to the right versus skewed to the left. So here, the bulk of the data is on the left, while this tail is being pulled to the right because of the outliers out here. So basically what that means is that your data is skewed in the opposite direction where most of your data lies. So you see how most of the data lies on the left side, so that means you're going to be skewed to the right. And then when most of your data is on the right side, this means you're skewed to the left. So basically, it's kind of weird and hard to remember at times, but I always look at the tail. This tail right here is more telling of where your data is skewed. So I see the tail, how it's going off to the left, so skewed to the left. Over here, my tail is going off to the right, so it's skewed to the right. And then this is a symmetrical distribution. So here we're tasked with trying to decide whether or not these are normally distributed. Normally distributed is basically it's symmetrical. Okay. I guess I should write that here. So this would be a normal distribution. Okay. Compare the distributions using either mean and standard deviations or 5-number summaries. Okay, so looking at the data presented here, so I'm noticing where my bulk of the data is on this side right here, meaning I get a lot of data up here, but you can see that I go off like that. So again, if we look up here, my tail is veering off to the left. So this would not be not normally distributed because it's not symmetrical. So it's not normal. Compare the distributions using either the mean and standard deviations or the 5-number summary. So in this case, it would probably be better to use a 5-number summary to find the center and the spread of the data. It'd be more accurate. Here, so if we take a look at this, now I know that we have this right here, but generally I would say that this is pretty normal. Like I know that we have a lot right here at 6. We have that mode that's pretty high. But generally, it's actually pretty centered. It's actually really not that far off from being symmetrical. I know that's a little high here, but again, that's really not too far away from the center. 6 isn't too far away from the center of data. So I would actually say that this is a normal distribution. And if it is skewed, it's really not by much, so I would just go ahead and stick with normal. But yeah, I would call this normal, and which means I would rather use the mean and the standard deviations. Yeah. Alright, so here, Now this one's a little bit tricky. Okay, so I know that we have a lot of the data right here on the right side, but you see how the median is more towards quarter 1 than it is towards quarter 3. Okay, so again, that basically what that's saying is that there's actually a lot of data pulling. There's a lot of variables that are pulling the median more over this way to the left. So that means that the data is more in favor on the left side. So what that means is that it's skewed to the right. Skewed to the right. Okay, it's kind of more telling with the median, where the median lies. If the median lies more to the left in your interquartile range, then you're skewed to the right. If the median is more to the right in your interquartile range, then it's going to be more skewed left. Again, it's kind of a weird concept to try and get down, skewed left and skewed right, so make sure you get some practice here. But no, this would not be normal, so not normal. Okay. Alright, so that should pretty much do it. Now there is a worksheet available to help you guys get a little bit more practice for statistics for a review. I'd recommend that you do that. I'm trying to decide whether or not I want to have it required, but just stay posted in Canvas. Take a look and make sure that you're looking in Canvas for that to see whether or not it will be graded or not. Okay, but let me know if you have any questions.